Hi everyone, this is Chapter 2 in your textbook, or a little bit of Chapter 3 on systems, and I'm going to be talking going a little bit quickly, but on the chemistry portion and then the positive and the negative feedback. So I'll go ahead and get started. It should only take a couple minutes. We talked about before that we have systems. You can see here's the example I used yesterday of the fish. The fish can be a system. You can look at its skeletal system. You can look at any type of digestive system. And look at all the inputs and outputs. Then, for example, if you want to jump down to an oceanographer, the system might consist of the currents and the climate as well as the weather patterns. And you can go a step further and looking at fisheries, and looking at the managers and the inputs and the outputs of the population of fish in that area. Now, looking at matter, we talked about open and closed systems. Remember, matter is anything that occupies space. Mass is a measure of the amount of matter that it contains, and weight is the force of the results from the action of gravity. Just a quick review on atoms and molecules. Remember, an atom is the smallest particle that can obtain the chemical properties of that element. Some of the elements that you want to be familiar with in this class are carbon, phosphorus, nitrogen, oxygen, silicon, and we'll get into a little bit more, but those are some of the few. Remember, compounds are molecules that contain one or more element. An example is sodium chloride or even water, H2O. They don't really test you on the atomic number, but you should be familiar with especially carbon, oxygen, and nitrogen, the main players of the game in this class. When we look at isotopes, isotopes are important when we look at radioactivity. And remember, this is the one that differs in the types of neutrons. Your protons and electrons are the same. An example would be carbon. Carbon has we have carbon 11, carbon 12, and carbon 13. Excuse me, carbon 12, 13, and 14. 14 is an isotope, and that is going to be radioactive. So when we look at radioactive decay, that's a spontaneous release of material from the nucleus that's unstable, and we look at that half-life. In this class, they've had some multiple choice questions looking at radioactive, especially with uranium, uranium-235, and that decays to a different type of element called thorium, or thorium-231, and that's its daughter of uranium. When we measure radioactive decay, we recorded the average of the decay and a quantity of that element, and that's called a half-life. And we're going to get to that a little bit later, but we look at nuclear power plants. They use this heat to produce the steam that turns the turbines to generate electricity. And we're going to get to radioactivity as well as half-life and isotopes a little bit later, but you're going to be able to calculate that radioactivity and the half-life on your hands, so be prepared for that. Remember your covalent bonds. Covalent bonds, you have two different types. Chemical bonds, you have two different types. You have covalent and ionic. Your covalent is one that's going to be sharing those electrons, such as water or CH4. You also have ionic elements that are going to be transfer of those, transfer of those electrons. Again, they do not go into the chemical bonding or transfer of electrons, but you want to be familiar with the chemistry of those chemical bonds so that you can then write about it in an FRQ. So here's an example of a chemical bond for the transfer. NaCl or sodium chloride is a good example. And let me go back real quick to water. Some of the properties of water, remember, it's a universal solvent. It's a weak bond, or those hydrogen bonds, or those van der Waals forces, I believe that they were called. It is a polar molecule, and where one side is more positive and the other side is more negative. Those electrons tend to hang out over at the hydroelectric side, over by the oxygen. We have different properties of water, and this is why they make it so universal. You have your surface tension.
Teacher students, just a couple announcements before we start. Refuel hour.
Keep going.
Freshmen,
Capillary
you will have
action.
a class meeting in the auditorium immediately when the bell rings.
See if I can pause.
Sophomores, you will have a class meeting in the auditorium
cohesion,
during the second
which is going to be your
refuel hour starting at 11:50.
Sorry. You have your cohesion and your adhesion.
Just
Adhesion is going to be the
lunch,
different types of materials, such as glass and water molecules that
deluxe cheeseburger,
attraction, and you also have capillary
my
action.
Favorite peanut butter cake. Come by the cafeteria today during your designated lunch time. Thank you.
Here's an example of adhesion with your bugs on water. Sorry about that. Again, some more properties of water. Your boiling and freezing points, you want to be able to identify those, and in water as a solvent. It's a universal solvent. Remember your acids and bases. Remember an acid is going to be the amount of hydrogen ions into a solution, and your bases are going to be the amount of hydroxide ions in a solution. So here's your pH. You should be familiar and know this already. Your 7 is your pure water. Going from 1 is stomach fluid. Cola beverages around 2, lemon juice and whatnot. And where we tend to talk about this is lakes and streams with the pH of water. If it's less, it might be more, it's going to be acidic. So here's some more pictures real quick. You should already know about chemical reactions. Remember your law of conservation of matter, where matter cannot be created or destroyed, it just changes form. And here's an example of a fire. It's going to release a lot of carbon dioxide. We may, as well as more even carbon into the air, because if we have deforestation within the trees,
proceed to your next destination.
Then we are going to have a release of that carbon from those trees, because trees are a great source of carbon. It's a sink. Some of the organic molecules that you should be familiar with in this class are going to be, NaCl, H2O, CO2, your phosphorus. These are examples of inorganic compounds, and they do not necessarily contain carbon, or they contain carbon but only bound to elements other than hydrogen. And a good example is carbon dioxide. Whereas organic compounds are going to be those that have that carbon-carbon bond. You have your carbohydrates, which are C6H12O6. Remember your glucose. You have proteins. They're going to be attached to a functional group such as nitrogen. They're called amino acids. Then you have your DNA and your RNA, which is very important, and you have your lipids, which is your biomolecules that do not mix with water, so such as fats, waxes, and steroids. One thing let me go back real quick with regards to lipids, is this was, I believe, one of your terms, bioaccumulation. A lot of pollution, such as DDT, bioaccumulates in the lipids. So it goes up the food chain. So as it stores up the larger animal chain, it's going to be storing more and more and more, ultimately getting to us. Okay, I'm going to skip the cells, you should know, but here's your single cell and your multicellular. Over here on the right, the shrimp. So in this class, the types of energy we look at is the energy is ability to do work, kinetic and potential. And that chemical energy that's stored in those chemical bonds is then they break and they form. So when we get to the energy unit, we'll talk about that a little bit more. Remember, we had our inputs and outputs the other day, your energy inputs and your energy outputs, and this is the first law of thermodynamics, is that it's not created nor destroyed. It just, you can't get something for nothing. Whereas your second law of thermodynamics
your flight is about to depart.
Is when that energy is transformed, it does not remain the same, but the ability to do work also diminishes, and that's called entropy. So we tend to lean more towards entropy as we move kind of down the line. So when we talk about food webs and food chains, you're going to be not having the amount available at the next station or the next trophic level. I believe in the next slide kind of shows you. Nope, it doesn't. And again, here's the second law again, where entropy, that all systems move towards randomness rather than towards order. Well, how does that flow into the environment? We talked about closed and open systems, so here's a nice picture and a review for you, where you have on the left your energy inputs of solar radiation and outputs, and that's going to be your open system, so both energy and matter can flow in and out, whereas a closed on the right, such as the Earth, you're not going to have those major outputs. However, we do have what's called a steady state, and when you have equal outputs is going to be, is said to be steady, so the amount coming in is going to be the amount going out. And those examples are your feedback loops. When the negative and positive do not refer to bad or good, they refer to the state or the perspective that you're looking at. So for example, in a negative feedback loop, that system is going to be responding to that change by returning to its original state. A good example is a thermostat. So if it's set at 80 degrees, what's going to happen is that the thermostat's going to kick in when the temperature of the room is higher. The air conditioner is going to go down and bring it back to 80. Conversely, if it's cold and it's set to 72 and it goes down to 62, then the heater is going to kick back on until it reaches 72, and then it's going to kick back on. So it's trying to go back to the homeostatic state or the original state in order to get balance. Whereas the positive feedback loop is when the change keeps increasing.
This flight has departed. Please enjoy your flight.
The rate at which the change is going to be occurring. A good example is going to be a woman giving birth. As you have your different types of hormone levels, like oxytocin and pitocin, they're going to be released, causing contractions. Those contractions are going to release more hormones, and those are going to keep going and increasing at that rate until the delivery of the child. However, the child is not going to be going back, so the human body, obviously, yes, goes back to the original state, but the child does not go back into the womb. So you have to think about perspective. Now, the two that I just gave you about the thermostat and birthing, you cannot use on the AP exam, but we'll talk about it tomorrow in class. But here's an example. Here's one on the lake level. You have a certain lake level. The level drops. Therefore, as the level of the water drops, you have a reduced surface area. From that reduced surface area, because you don't have that much water, you're going to have less evaporation. If there's less evaporation, therefore you're going to have more water and the level is going to start to rise. So it's going back to that original state. However, on the right, we have a positive feedback loop where if you have a population increase, all those people are going to have children. So as they have more children, then the population is going to increase. Then those children are going to have more children, and the population keeps changing until something might change it, but it will keep going until they're at the carrying capacity, there's disease, run out of food, etc. And that is it. See you tomorrow. Have a good night.